Welcome all to this workshop for Hexa-X at this ONDM 21. Today we will present the Hexa-X vision on 6G by Mikko Uusitalo and myself, and then we will have a few presentations from invited speakers describing aspects from the optical networks. So I'll leave the floor to Mikko to begin.
Thank you, Patrick, and thank you to the organizers for making this possible. And let me start sharing my slides just a moment. So hope you can now see them and hear me well. So I'm Mikko Uusitalo, coming from Nokia Bell Labs Finland, leading a radio research team there, and then also leading this Hexa-X, so European 6G flagship project, and would be happy to give you the overview of the project and our vision. Start with that. So if you look at the earlier generations, here you can see some information on the important parameters with respect to them, about the frequency range and bandwidth, computing platform, networking platform, and copper access. This development has been quite dramatic over the years, and what one can do with the wireless cellular technology generations has been showing quite some tremendous benefits for society, for all the end users. The defining applications, so 4G really brought mobile internet to every pocket, and with 5G the defining application visible is then industrial Internet of Things, so providing the kind of next level of connectivity needed for machines and for all sensors, and for us from this perspective. The unexpected application remains yet to be seen for 5G. Also, there are many things we need to pay attention to how 5G moves forward. But however, it is time already to start looking at 6G, as we and many others active in 6G have been showing. In all these generations in Europe, there has traditionally been a project or a set of projects playing a fundamental central role in defining creating the basis for the new generation. And then, as we are the European 6G flagship project at this stage of development, so we are aiming to have similar role for ourselves. So about our vision, we have a vision to connect three worlds, human, digital, and physical worlds, with the fabric of 6G key technology enablers. So we humans need to be in efficient real-time control of the physical world via efficient human-machine interfaces. Also, then models of us humans are being built in the digital world to be able then to do, for example, preventive healthcare, predict heart attacks before they take place. And then we need also efficient connection between the physical and digital worlds in order to be able to take these digital twins to a much wider extreme towards massive twinning, to be able then to better operate, design the physical world with the help of the digital world. So then there will be more on the use case and use case families in the next presentation, but based on the vision we have identified use case families, and then based on this work we have then identified that what are the research challenges that we need to tackle towards 6G. And sustainability is central, so 6G needs to be sustainable, and we need to look how can we have 6G for sustainability. How could we use 6G in other sectors of society for sustainability? Network of networks, so was talking about measuring body parameters, looking at the networks of a person or set of persons or machine or set of machines, going and looking at the different architectural enablers, and going to have all these networks function collectively as a network of networks. So how are we going to best arrange this? Connecting intelligence, so 6G is the first generation where we can see that if we use AI ML as a fundamental base for the new generation, so how would the new generation look like? And trustworthiness, so as more and more aspects of life get digital, get wirelessly connected, so trustworthiness is very central also for the acceptance of the technologies. So that needs to be taken into account from the very beginning of the design of the new generation. Extreme experience, so taking the key performance indicators of all the previous generations to the next level, and central as the increase in traffic has been quite significant year by year. We have been talking, for example, about the increase 50 to 100% in wireless traffic. So then, how do we address this and other challenges of moving forward the earlier key performance indicators? Global service coverage, referring to sustainability in terms of getting everybody a possibility to have access to digital services, as well as then providing the services in also very remote locations. So how do we then address these? What technologies do we need to pay attention to? Here in the center we have 5G and 5G enabling technologies. In the outer rim we have the research challenges I just went through. So then what kind of technologies can help us, for example, to increase further the capacity of the network? So there we need to see how to cope, what to expect to get from going to higher frequencies. And at the same time, we need to pay attention to also low and mid bands. We need to pay attention to, in addition to communication, what other information can we get on the side related to localization, sensing and mapping, AI ML as a fundamental base of new generation, and many other technologies that we are studying in Hexa-X. So in this radio performance, we are looking at these new frequencies with respect to that radio channel modeling for those, what kind of waveform modulations might be needed, what kind of hardware technologies would be available, and what could we expect to get out from those. Distributed MIMO, so the trend of increasing amount of antennas and also physically separating them, but them working together. And in this 6D high resolution, so looking there about this sensing opportunities. On this AI ML as a fundamental base, we need to look at that what could be done there at the lower layers of the radio and also on then the higher layers. And on this network evolution, need to look at the different new architectural enablers, what can they provide, and the role of AI, ML, and what is needed from the different vertical perspectives. We are a strong consortium, so vendors are leading. Nokia is leading the project with Finland and Germany from Nokia side. Ericsson as technical manager. We have strong operators, Orange, Telefonica, Telecom Italia, Siemens representing the verticals, other verticals represented by advisory group structure, strong technology players, and then high quality academia. Timeline, so Hexa-X started beginning of this year, running for 2.5 years. This is the time of 6G structuring and framing. Then hoping to build the base for a much wider set of 6G projects moving towards systemization and halfway through the decade to standardization and end of the decade decade then to commercialization. As said, there is many active players around the world. In Europe, then the smart networks and services is the next set of projects. There is also national activities like in Finland and Germany. In North America, NextG Alliance and some academic funding in cooperation with National Science Foundation, as well as very strong initiatives and actions in Asian countries as well. On this sustainability, so still to highlight that is one of the core values in Hexa-X and something we need to pay strong attention to. And here we are paying attention to why the United Nations Sustainable Development Goals, and according to those, seeing that how can we address and contribute to society for addressing these goals. And as said, 6G needs to be sustainable. We need to look how can we make sustainability with 6G, so 6G for sustainability, other sectors of society where we can contribute. So thank you. That was the introduction to our activities.
Thank you, Mikko. We have time for a few questions. So if you have any question, just unmute or write the question in the chat.
This is Paolo Monti. So maybe just a quick question on, you mentioned sustainability as one of your direction or KPI for research. So do I assume correctly that you will be looking into more than just energy consumption of your solution?
Yes, it is like a central thing to try to look all the different aspects. In addition to energy efficiency, it might be like limited what we can do, but here we need to pay attention to like materials efficiency and also carbon emissions.
Okay, thank you.
If there are no further questions, maybe we can move on and you can address your questions to the panel at the end. The next presentation will be by me. I will present our use cases and KPIs and KVIs. Let's see if I can share the screen. Can you see my slides?
Yes.
Okay, so welcome. My name is Patrik Rugland, and I'm the technical manager in the Hexa-X project. And I will present the use cases and key performance and value indicators. To begin with, I will present our envisioned use cases for 2030. And in the project, we've identified many different potential use cases, as Mikko showed earlier. And to simplify the analysis, we've grouped these use cases into several use case families. And the first one is what we call sustainable development, looking at how 6G can be used to address the UN Sustainable Development Goals. And as you asked now earlier, this includes both environmental aspects, but also other aspects such as digital inclusion. The second use case family is what we call massive twinning, looking at how to take the concept of digital twin from 5G to the next level, both in industrial applications, but also for society at large. The next one is what we call telepresence, looking at how to take the extended reality currently being defined for 5G in 3GPP into the next generation. And that is here to be able to experience the world remotely or interact with virtual objects with all of your senses. The next one is the so-called robots to cobots, where we see that the development and deployment of AI and robots will continue and increase and will evolve into much more advanced and complex systems that will be able to interact and collaborate with other robots, but also with humans without direct supervision of humans to solve complex or dynamic tasks. The last one is more of a collection of different use cases, where we see a need to be able to enable local network with utmost performance or security at a low cost. Naturally, you could deploy these custom-made solutions to solve a particular problem, but to be able to do that at a large scale, it needs to be possible to do this in an automated way. And finally, we acknowledge that this list is far from complete or exhaustive. We may have missed a few use cases. Others will be extensions of existing use cases, and other stills will not be invented until the 6G networks are deployed. So to look a little bit more in detail on these use cases, I will present one representative use case from each of these families, showcasing some of its key aspects. The first one is for the sustainable development, so what we call the e-health for all. The idea here is in order to foster a sustainable world, digital inclusions will be imperative. And one aspect of that is to provide access to healthcare to everyone. And how this applies to 6G is that you do it with medical consultation and treatment. And this means that it will be important to provide affordable connections to everyone in rural or remote areas, as well as in underprivileged groups in affluent areas. Of course, in affluent areas, the users will be able to access even more advanced healthcare at home using more advanced devices. However, in rural and remote areas, even traditional healthcare can be improved by employing AI or XR tools to assist healthcare workers. In addition, with the proliferation of devices, it could be possible to collect data for population-level health monitoring or disease prevention on a large scale. But in order to achieve this, a key requirement will be to reduce the cost, both of the devices as well as the network deployment and operation. The next one is the massive twinning, where we look at the immersive smart city. Here, the idea is to take the concept of digital twin and apply it to a whole city, representing it in an accurate, real-time, four-dimensional spatial-temporal map, where you have sensors and actuators everywhere that enable accurate planning or monitoring and management of the city. And you can use physical modeling of the digital representation to do forecasting. And the applications for these are wide-ranging and could include management of utilities, public transportation, healthcare, or environmental monitoring, etc. And to achieve this, it will be important to employ distributed compute to reduce the latencies and not having to shift all the data to a central node. And AI ML tools will be required to analyze all this required data, all the data. For the telepresence and the fully merged cyber-physical worlds, the idea is to bring the virtual and augmented reality to the next level. And the idea is to allow the user to experience digital objects, environments, as if they were real and part of the physical surrounding. And this will require applications to adapt to the user and the physical environment in real time, to avoid collisions and to get proper occlusion of objects. To achieve this use case, novel devices will be required to capture and render all of the senses in a power-efficient way using untethered devices. And in order to keep these devices lightweight, the network will need to assist by handling most of the processing of the spatial map to create these digital experiences. For the robots to cobots, we will, for instance, be looking at interacting and cooperating mobile robots. And this is a natural extension of the development of AI and autonomous systems, where there will be a need for massive amount of robots to interact and self-organize to collaborate and solve complex tasks. And as I mentioned, this collaboration will both be between robots, but also between robots and humans without any direct supervision of the robots. And this can set strict requirements on the reliability and safety and latency and positioning accuracy. For instance, in case the robot's trajectories are blocked or modified, it still needs to operate safely. And finally, we have the use case family local trust zones, where we, for instance, will be looking at what we call dynamic and trusted local connectivity. The idea is that you may have scenarios where a temporary application would require significant performance, either in terms of throughput or latency, or in regard to reliability or privacy, which could not be economically feasible to provide with a wide area network. This could, for instance, be a body area network during surgery, where you have multiple sensors or devices inside the body connected through a local hub, or during autonomous harvesting campaigns where the machines are connected with each other. And it requires tight coordination between them, but there is no need for remote control if the control functionality can be onboard locally. And of course, these dedicated local area networks could be deployed as it is today. But to reduce the operating cost and deployment cost, the deployment and management will need to be further automated and would require self-adaptive networks relying on, for instance, relay or mesh networks or device-to-device communication. And to provide the necessary capacity, provisioning of local spectrum use with, for instance, spectrum sharing or automated spectrum licensings would be beneficial. Next, I will present some of our thinking on the key performance and value indicators. To analyze the required performance, we have looked at existing KPIs and tried to see how these could be extended. To define these indicators, we have done both a top-down approach, looking at the use cases, as well as a bottom-up approach, looking at what capabilities technologies can provide. And in order to avoid an unnecessary race for sticker price performance, where 6G would simply be X times 5G, we have started to take a much broader look at the KPIs and have divided these indicators into different categories. The first category is the extension of traditional KPIs, where, for instance, the achievable peak rate is extended toward terabit per second. Looking at the connection density, this does not necessarily have to be extended beyond what 5G can be delivered, but it will need to be at least on par with it. For traffic capacity, the increased data rate needs to be accompanied with a corresponding increase in network capacity. And finally, location accuracy introduced in 4G will continue to be improved. However, some of the existing KPIs will need to be reconsidered from a more holistic end-to-end view. For instance, the energy efficiency will no longer suffice to only look at the device or power node consumption, but would rather need to look at the whole network on how to minimize the total energy consumption. And in addition, it's not particularly beneficial to push the air interface latency down far below 1 millisecond, as long as the rest of the network cannot even provide tens of milliseconds of end-to-end latency. Instead, it's more beneficial to optimize for guaranteed bounded latency with minimized jitter end-to-end. For the availability, it's not only to minimize the downtime of the radio link, but instead to ensure that the end-to-end service used by the user can continue to perform satisfactorily, even if the network would have to reroute the service on the fly. For the coverage, it's not only the radio link budget we need to optimize, but rather looking at how non-terrestrial networks could be used to provide truly global coverage. Next, we see that 6G will be extended with new capabilities well beyond connectivity from earlier generations. For instance, the higher carrier frequencies expected will enable to use the communication radio signals as a sensing signal. And we expect that computational resources will be widely available in the network in order to offload computations from the devices and to flexibly manage the network operation and varying loads. We also see artificial intelligence will be an integral part of 6G networks, both in terms of automating and optimizing network performance, but also provide AI services to operators and end users. In addition, we see a need for an extension of maintenance-free devices that can be embedded anywhere without the need for a power supply or battery change, for instance, using energy harvesting. For each of these new capabilities, we see that they can improve on the traditional KPIs, for instance, using sensing to improve beamforming or initial access, or using local compute resources to reduce latencies. However, each of these capabilities also introduce new domain-specific KPIs, such as computational round-trip time or AI model accuracy. And finally, we have identified a number of requirements that we call key value indicators, which intends to capture the more fundamental values that 6G can bring. For instance, one of the main challenges for the future is how to create a sustainable world. From Hexa-X, we see that this needs to be addressed in two distinct ways. First, the sustainable 6G, how to make sure that the 6G systems minimizes its own environmental footprint in order to stem the increase in power consumption coupled to the exponential increased data volumes. But we also see that 6G for sustainability, where 6G has the opportunity to radically impact our society to enable sustainable developments in many other fields. But there are many other aspects of sustainability as identified by the United Nations with more intangible aspects, such as inclusion, access to healthcare, education, and strong democratic institutions. For this, 6G can help bridge the digital divide by ensuring that security and trustworthiness are considered already in the design of 6G systems, we can ensure that this will not be an optional feature. Finally, in order to be able to deploy, operate, and scale these 6G systems to address the diverse use cases, as well as to foster further innovation, it will be important that the 6G systems will be flexible both in design, architecture, and operation. So to look at how optical networks can play a role in these 6G systems, I quickly show a slide here mentioning some of the main aspects of optical technology for transport networks that are applicable for 6G. We see that optical networks is a promising technology to deal with these requirements, thanks to the capabilities to support high bandwidth and low latencies. And we see that the evolution of 6G will be stepwise, and the several services will be mixed according to the needs. Therefore, the transport networks based on optical technology can guarantee transparency to any protocol and the sustainability for any protocol splits, and can be used in, for instance, backhaul or fronthaul. And if this is combined with normal packet switches or routers, the granularity of the optical transport can be tailored to specific use cases. Of course, in some deployments, it's more cost efficient to deploy passive optical networks. Anyway, as you most certainly know, there are some challenges to be addressed. The 6G scenarios will often be quite dense scenarios, and there will be a need to provide cheaper equipment with smaller form factors than what is available today. Furthermore, it's very relevant to consider equipment for transport that are plug and play, which will allow the network operators to reduce an inventory costs as well as configuration in the field. Finally, full tunability of the equipment and possibility to reconfigure remotely is very important to scale up transport networks that can dynamically provide connections. So I will not go into more details on these aspects, but just remind you of some of the aspects of the main benefit to use optical networks. And more details will be given in the invited speakers. So thank you all for your attention. So if you have any questions, please unmute your microphone or write the question in the chat. No questions?
I might have, again, this is Paolo. I don't want to monopolize the questions here, but I mean, it's quite interesting what you said with respect again to energy consumption and optical networks. So, I mean, in past studies, it has been shown that whenever you have a multi-layer network, basically the culprit or the most consuming layer is actually the packet switch one. So in order to minimize this energy consumption, is there in your roadmap an idea of relying more and more, I mean, relying less on packet switch technology and more just on transparent optical connection?
I don't have the answer to the roadmap on the optical networks. Hopefully the optical network experts following me will have a response to that.
Oh, okay.
So if there are no questions, I will leave the floor to Fabio Cavalier from Ericsson, and he will present optical technologies for new generation mobile transport networks.
Thank you for your introduction, Patrick. I will try to share the screen. You see the screen?
Yes.
Yes.
Okay, so let me go in. Info. Okay. Yeah. So I will provide more detail as anticipated about optical transport network. Mobile transport network, so-called mobile transport network, is a completely new segment. And you can see a picture here taken from a new ITUT recommendation on that. It is characterized by short distances as in an access network, but very high capacity and multiple topology as in wide area networks. And in addition, has new features like self-configurability and low latency, as pointed out in the previous presentation. This has several consequences for optical components, because it is true that potential product volumes are high, as in datacom, but the target loss is low, as in access, and this is very challenging for starting a new business. So standardization of multi-source agreement pilot line will play a role in making successful this new segment. But let me talk a little bit more in detail about these new optical components that are needed. Self-tunable optical transceivers, for instance, they will enable network automation and operational simplicity. Very cost-effective, 25 gigabits per second, so-called gray optical transceivers, cost-effective coherent interface. And there is space also in this new segment for expanding the domain of direct detection optical interface beyond 25 gigabits per second, so to cover the bit rate for 50 to 200 gigabits per second. I will present some enabling technology like new modulation format, tunable chromatic dispersion compensators, advanced receiver architecture, and other components enabling automation in the network are small form factor, cost-effective, reconfigurable optical drop multiplexer, for example, based on silicon photonics, and tunable optical filters based on silicon photonics as well. I will provide an overview here, starting from the transceiver. These are possible building blocks of a new transceiver modulation. You may use conventional plane OK modulation, but also advanced modulation format that have spectral efficiency like PAM4, but much better performance. I will show an example later. You can compensate for chromatic dispersion, which is an impairment due to propagation in optical fiber, and you can do so in a sustainable, let's call it, way, without power-consuming electrical equalizer, but in the optical domain by means of silicon photonics microring. You can also use advanced receiver architecture, stocks receiver front end, to further increase the capacity of the channel. Okay, we'll not go into the detail. This is the ODC optical dispersion compensator. This is a sequence of microring resonators, and with a very simple structure, 3 microring. Here there is a snapshot. You can compensate more than 25 kilometers of fiber, 25 gigasymbol per second, so 25 gigabits per second, okay, or 50 gigapan4. And an important feature that you can compensate with the same device all the channels of the spectrum, and you can cascade these devices to further increase the distance. Here is some measurement. As you can see, with the on-off keying, it is not possible to cover more than 4 kilometers with the very high penalties, or even less. While with this device, you can extend the reach to 15 kilometers, even more, which is far enough for fronthaul, for instance. And with PAM4, you can further increase the distance. Advanced modulation format, these are an alternative way, or a complementary way, I would say, to increase bit rate without challenges so much the electronics. So keeping a low electronic bandwidth and having high resilience to the chromatic dispersion. Again, I will not go into the details. There are published papers, but I will just show some performance here. You see with this yellow curve that you can cover with quite a small penalty, 15 kilometers again, and you can see the huge performance gap that there is with the PAM4. This is PAM4, green and red curve, and you can see here what happens when you use this modulation format. You gain a lot of dB from optical signal to noise ratio. And you can see also in this red curve on the left that electrical pre-distortion, for instance, performs very well, but is very selective. So you have to tune the device to the actual link distance, which is not the case for this device. Okay, you can increase further the complexity of your transceiver. I will not go again to the detail. We achieved excellent results, 24 gigabit per second transmission over 10 kilometers in C band, so in the conventional WDM band. But at this stage of complexity, you may wonder if the cost is low enough to compete with coherent transmission. I don't have the answer. So these are competing technology at this bit rate, in my opinion. We also performed in the literature. You can find some research about cost-effective coherent transceiver front end. Here you see an example that just use a coupler at the front end, and you can see that the performance is not so bad, even if this is before a forward error correction, of course. And of course, also here you need some digital signal processing, and this is not without drawbacks. In particular, the electrical interfaces at this point is quite challenging, but this is a work in progress. Finally, integrated and reconfigurable optical drop multiplexer. You can see here an example that we have developed as a prototype. It consists of several micro rings. You can adjust the micro rings to select a specific wavelengths. You have a switch to select the direction where the wavelengths come from. You have attenuators to equalize the channels. Preliminary tests, I would say, are encouraging. Very good rejection to the adjacent channel. Good tunability efficiency. And very recent result, the device was able to let 100 gigabit per second channel over two polarization passing through. That means that is compatible with current advanced transceivers deployed in the optical network. Okay, but when all this will become reality, the problem is not technology. Technology is mature enough, but the optical component market is a healthy but quite fragmented market. You can see here that even the biggest vendor of optical component is not a so big share of the whole market. It is dominated by telecom vendors where volumes are moderate and the cost higher, and datacom where the volume are higher and the cost lower. So the question is where 5G transport and even more 6G transport will fit in this market. And again, this is an evolution we are seeing. You will launch together with our friend of Nokia an initiative called MOPA, Mobile Optical Pluggable Alliance, that is aimed at making the market more aware of the specific need of the mobile transport network. And my last slide is that, again, the major challenges are not with the technology in this case, but with the ecosystem. Full vertical integration or, let's say, full outsourcing will not work in this mobile transport network, and probably we need some different cooperative model among the various players. So components vendors, system vendors, operators, so university, and so on. So also this is an evolution we can driving and also seeing. We will see. We will see where it will bring to. And this is what my last slide. Thank you very much.
Thank you, Fabio. Are there any questions from the audience?
If not, Patrick, I can probably take the previous question from Paolo about the switch.
Go ahead.
Thank you. So, Paolo, it is my view that packet switches and optical switches will coexist eventually, massively in future networks. So this when you need to trade off between latency, capacity, but also statistical multiplexing, this is the only solution. So a pure big optical pipe will not guarantee statistical multiplexing, will be quite inefficient. So it will be energy efficient in itself, but not energy efficient if you look at the whole network. While on the contrary, pure packet switches could bring some performance issues in congestion situations. So I see that mixed hybrid architecture will be successful in this scenario.
Okay, thanks, Fabio. So where then the energy savings or the improvement in the energy performance then would be more at the device level, trying to make them singularly more energy efficient?
As I said, there are various possibilities. Performing in the optical domain features that today are performant in the electrical domain is a way, and I've shown a specific case, the optical dispersion compensator. Of course, there is always a cost for everything. You cannot pretend the same performance. So these kind of devices work well over short distances, but you cannot pretend the degree of reconfigurability and the distance you can achieve with an equalizer and a coherent optical interface. This is just an example, but similar considerations for other components like the reconfigurable optical ONDM I show. So it's always a matter of trade-off between performance.
Yeah, of course. But thanks. It's always like a question that is in the back of my mind. So yes, thanks.
And there's a question from Tommy.
Yes, thank you for interesting talk, Fabio. I'm not, I have background in physics, but I don't really know the processes and the materials used now. You mentioned these optical amplifiers. I'll be curious about how scalable is it? How is the footprint and environmental footprint on these processes? If we think about 6G should be sustainable compared to electrical community. Do you have any, no detailed numbers here, but do you have any gut feeling on where we're going? What's possible?
Yeah. More than a gut feeling, but it will be a long discussion. So today, optical amplifiers used in optical network are quite bulky because they are fiber amplifiers based on coils of fiber. And you can make it quite small, but you can't integrate it you can integrate the optical amplifier in a transceiver, for instance. You can do so if you use semiconductor optical amplifiers. Semiconductor optical amplifiers are like any semiconductor device, can be integrated for it in other devices like the transceiver, like a filter, and so on. But have a drawback that are very sensitive to the crosstalk between the different channels in the networks and are also nonlinear. So not always the use of this kind of semiconductor optical amplifier is suggestible in a complicated network. Again, this is an open point, and I will say that nobody today worldwide is covering this research very actively. There are many people that speaks about new bands, new optical amplifiers, but I didn't see any new research on this topic. So today, networks still rely on bulky erbium-doped fiber amplifiers that have excellent performance, but have some drawback in cost more than in energy efficiency. So it's, they consume some watts, but what is a bit of it is that in an access side, their cost is not needed. This is probably an area where research should be more active.
Okay, thank you.
Thank you, Fabio.
Thank you.
Let's move on. If you have any questions, you can post them in the chat and handle it there. Let's move on to the next presentation by Dr. Carmen Machuca from TU Munich in Germany on efficient optical core networks.
Thank you. Can you see my presentation?
Yes.
Yes, okay, perfect. So thank you very much to the organizers for the invitation. Today I will discuss which are the requirements of optical core networks and some of the solutions towards the efficient use of these optical resources. This work has been partially funded by the Opticon project, so I am not part of this Hexa-X project. And this Opticon project was funded by the German Federal Ministry of Education and Research. And these are our partners together. So this work was performed also with HADPA. Okay, so with the advent of 5G and the foreseeing of the next 6G, as it has been already presented, operators have to deal with the different requirements of optical core networks, which are in fact becoming very demanding. So in terms of flexibility, as you know, current optical core networks are rather static. This means that once you set a light path, usually it's kept unchanged and for several months or as long as it is required. And in order to keep with this increase of demand changes, operators in general, they over-provision these light paths so that they can cope with this increase of traffic. But this is quite limited solution, and rather the operators will prefer to have more flexibility so that they can dynamically set up light paths and use the resources in an optimal way according to what it is demanded. The next one is the reliability. So, as you know, one of the key issues of reliability is the high availability, which is required, even more than 6 nines for 6G. And of course, this high availability relies on the reliability of the network components, but also on the used protection and restoration schemes. And also, it is more relevant for restoration schemes. In general, fast and accurate and efficient fault detection and localization methods are required. And all these methods, of course, depend on which is the monitor information, which has been shown to be large, rather large, as you have several monitor parameters for every active component. And this huge amount of monitor information is pushing machine learning techniques as one of the solutions to be able to solve this fast and accurate fault detection and location. The objective, of course, is to reduce metrics such as the false positive or the false negatives for the fault detection, and also an efficient location of the failure for the failure localization so that you can use restoration techniques in an efficient way. But of course, we do not have also, so we have to distinguish between hard and soft failure. So a hard failure will be, as you know, the failure the fiber break. A soft failure will be the fiber bending. But we also have to cope with different attacks or disasters and even bugs, since we have now software-based optical networks. And last but not least, we also have to consider this technological sovereignty in order to be able to plan and invest in the right number of components and vendors, such as we reduce the dependency of certain vendors that in the future may cause an issue. Regarding scalability, as you know, 5 and 6G increase significantly all these number of end devices, as it was already mentioned at the beginning of this workshop. And also this increase of services and demands is triggering an increase of traffic. It is true that most of the research on this topic has been focused on radio access networks and front-haul design, assuming that the core network is sufficiently provisioned to meet this increase of traffic. However, although this assumption may still apply, we cannot assume that this will be like that in the following years, and we have to look into schemes that are really going to cope with this increase of traffic and devices. I also mentioned here the green technologies, which is also related with the discussion we had on the power. So as you know, ICT has a huge share of this global electricity usage. And also in optical core networks, we also have to look into decrease the power consumption. So also some energy saving techniques are being considered. So for example, to adapt different modulation in the transceivers so that you use the modulation format accordingly and you use the right power consumption. So you can reduce instead of using higher modulation formats. Of course, there are other requirements like security, latency, and so on that I'm not going to consider in this presentation. Okay, so a bit regarding this optical technologies evolution. As you know, current networks are fixed grid. This means that you have all these channels aligned to a given grid. Usually we use this 50 gigahertz grid. And this fixed grid solution, of course, now it is quite is easy to be designed because mainly doing the routing and the wavelength assignment with some wavelength continuity constraint, you are able to find which is the right wavelength for every demand. In case the demands increase of bit rate, then you can keep using the same bit rate and increase the data rate of the demand. Of course, then the idea is that you have a limit of the bit rate that you can transmit for every light path, which will be determined by this grid spacing. And also you have to keep in mind that you have to keep also some word space between the different channels. So you still have limited in the number in terms of the bit rate that you can transmit per light path, and also you have this some waste spectrum. So finally, below you have this flex grid that you can support thanks to the development of these bandwidth variable transceivers, which allow to configure several parameters like a bit rate, modulation format, forward error correction, and so on. And each of these configurations, so the combination of all these parameters, will be also associated of how many frequency slots you will need to reserve in your spectrum. And also, which is the minimum OSNR at the receiver side. So what you have to consider is that in this spectrum, you will have then narrower slots of, for example, 12.5 gigahertz. And then depending on the configuration, you will need a particular number of these frequency slots. And then the use of this bandwidth variable transmitter will allow you to have an improved spectrum utilization and therefore a higher throughput compared with the fixed grid. In general, we are going to consider these bandwidth variable transponders with bit rates ranging from 100 to 600 Gbps and different modulation formats. Okay, so if we look into the core network, in general, core network, we consider that it's a set of interconnected nodes, and the nodes are hosting ROADMs, which are then interconnected through these optical links. And optical links, we consider that is a set of heterogeneous spans and amplifiers. So the spans, they have some range between 50 and 120 kilometers and separated by these amplifiers. In this, initially, we are going to consider that we have the single core fibers and C-band. Also, we are going to say later that, we can also use this band division multiplexing and this or multi-core fibers if you want to increase the capacity of your network, as this is going to be also addressed in other ONDM presentations. Okay. So here, triggered by the 5G, 6G expected traffic increase, but also, as you can see here, we have the Cisco traffic forecast for residential customers, and also from data that you can gather from Internet Exchange. In general, there is going to be a traffic increase of around 22%. But this is just based on the predictions, but also you can have some unexpected events like we had last year in COVID, which, as you can see here, it can cause an increase of the traffic. And operators, they have to cope with this unexpected increase of traffic. So their network dimensioning is not only based on the traffic forecast, but also they have to go with this unexpected traffic increase. So which are the issues that core network operators are facing? So the first one is how to model realistic traffic increase. So of course, they have to consider which are the traffic parameters they have to include. So the number of data centers and the traffic of these data centers, which are the number of internet exchange points, which is the population distribution in the country, etc. And also how to propose a model that is able to cope with these unexpected events. The second one, how to cope with increased cases. So the question is, are there enough resources to cope with this traffic increase? In fact, this is part of the network planning, so that you need to have in the field already enough resources, enough equipment in place to cope with this increase. And in the worst case, in general, when you have new traffic and you cannot cope with the light paths that you have set in your network, in general, you may install new light paths, but of course you can assume that this is a quite expensive solution because it's a waste of the spectrum and also an increase of the cost. So we are going to see how FlexGrid will allow to increase this throughput per device invested, and also how to increase the flexibility by the reconfiguration of these BVTs. Another issue that the operators are facing is how to reduce or to block, to reduce the block or the partially breach demands. And you have to think about that these are mainly the revenues, and every unhappy customer on every demand that is not possible to be configured or to be set is going to cause a reduction of the revenues and obviously a reduce of the benefits. So the idea is to increase the spectrum utilization efficiency such that, so when you have an available spectrum, so either you are using the C-band or the C+L band, you have to have as high utilization efficiency as possible so that you can cope with the maximum number of demands given your available spectrum to increase also your revenues. And last but not least, also to keep all the benefits high, the idea is to reduce all your investments. So either you increase the number of transponders, or you add fibers, or you use other bands and so on. But the idea is always to keep with all these demands with as least investments as possible. Okay, so mainly, we are going to focus in this routing configuration and spectrum assignment problem. The idea is that given a network topology with all these components and the link information, such as which are the ROADMs, the amplifiers, the span lengths, and so on, also given these demands, that is the traffic model, how this traffic is per year, and also which are the different configurations which are possible in your BVTs, is to find for each demand, which is the set of light paths. And by light path, I mean the path configuration and spectrum. So a demand, in fact, can have more than one light path. And why? Let us consider, for example, a demand of 400 Gbps. It could be initially mapped to one light path only of 400 Gbps. But if the path is too long and you don't have enough OSNR at the receiver, you may have to set up two light paths of 200 Gbps. But if the distance is even larger, as for example, you could have in the USA in order to interconnect the East with the West Coast, you may have to set 4 different light paths, 100 Gbps each. So this is mainly the concept that one demand can be associated to several light paths. And which are the constraints? So the first thing is that we want to minimize the number of BVTs. And why? Because in general, BVTs are really the ones that are causing an increase of cost and also of power consumption. So mainly reducing the BVTs will also reduce the cost of your solution and also the power consumption. Furthermore, as explained before, each BVT configuration has different minimum OSNR, and this minimum OSNR has to be guaranteed at the receiver size. So hence, based on the path length, the maximum bit error rate can be determined, assuming that you don't have any regenerator. For this OSNR calculation, mainly we have considered enhanced Gaussian noise models. So even you have a fast calculation based on the ACF EGN, or you can have a more accurate but quite heavy computational type, which is this FFEGN. Another constraint is, of course, you have to guarantee the bit error rate of the demand is offered. So the sum of all these bit rates of the light paths associated to each demand has to be at least the bit rate of the demand. And also you have the spectrum continuity constraint and the spectrum contiguity constraint that is mainly to make your spectrum assignment easier and to avoid any segmentation. And finally, for the performance of the proposed solution, you have the number of block or unsatisfied demands, which is your network throughput, which is the spectral efficiency, and which is the cost and the power consumption of your proposed solution. Okay, this could be the RCSA problem for one particular year, but in our case, we are considering the multi-period RCSA problem. So we have all this traffic increase, which has been foreseen for the following years. This is just one particular requested traffic model. Of course, you have to run it several times, and every time you will have different traffic increase. And now what we want to present is how the operator could cope with this increase of the bit rate of the demands. So let's start with the first one, is to say, okay, if my bit rate is changing from 200 Gbps to 400 Gbps, I could initially just reconfigure my connection, but because with the 400 Gbps, since it has a lower minimum OSNR, I cannot cope with that. So one solution, this is the first one, is mainly to add regenerators. So if you add regenerations in the network, this will allow you that each light path can be configured with higher bit rate. And as you will see in this presentation, which will be done later in the ONDM, in this ONDM, we have seen that when using this regeneration, the number of BVRs can be reduced even 25% compared with no regeneration in the network.
Excuse me, Carmen, how much further do you have? If you can wrap it up.
Okay, I will go fast then, sorry. Okay, the next one will be this use of C+L bands or to add more fibers. And here we have just a very first scenario where we have compared the benchmark scenario of having one fiber and only the C band here on the left with respect using only RDM, so that is adding M fibers, or using C and L band, or using both M fibers and C+L band. So we have seen that, of course, there is a compromise in terms of which is the throughput, which is the number of allocated demands, which are the number of fibers per link which is required for the SDM case, and which is the average spatial efficiency. Then, last but not least, I will focus on this option, which is mainly to compare either to upgrade the configuration of existing LiPad demands, add new LiPads, or reroute existing LiPads so that you can improve the efficiency. And I just give you here the references. The last one that is combining these methods from the power point of view, again, related to power. This is a presentation that will take place tomorrow morning. Mainly, which is the impact of these three alternatives. So approach one is mainly only to reconfigure the existing LiPads to cope with this increase of bit rate. The second approach will be to upgrade, but also to add LiPads whenever is required. And the third approach will be, if even adding LiPads is not possible, then we will try to reroute existing LiPads so that we can cope with more LiPads at the end. So you can see here on the left that approach number one is saturated in 2024. Approach 22 is not able to cope with this increase of demand in 2028, but with our proposed third approach, we are able to cope with this increase of traffic in a smooth way. And here you have a distribution of how many upgrades, how many additions, and how many rerouting actions we had for each of these approaches. So with that, I will summarize my talk. So mainly what we have addressed is that 5G, 6G will keep increasing, which are the bandwidth requirements of all these demands. We have seen which are the issues that operators are facing. So mainly we have to go with all this increase and optimize or increase as much as possible all this spectral efficiency. And of course, trying to combine to go with all these requirements while minimizing the cost. So thank you very much for your attention.
Thank you, Carmen. I believe we have time for one short question. Everyone's shy?
No questions.
No questions. If not, then thank you, Carmen. And we can move on to the next presentation by Dr. René Bonk from Nokia, Germany. And he will present the industry view on optical network aspects.
First of all, I would like to highlight here as well the people I have discussed this work with. So it's the industry view on optical network aspects. Of course, I have to say, right, let's first of all, not speaking about the entire industry. I think I can focus first on the Nokia Bell Labs view here, looking more on the optical access part. Let's start with what do we talk about? And we have seen a lot of use cases and requirement for 6G about more capacity, better coverage, lower latencies in the millisecond range, more virtualization, critical network availability, and new architectures. And so one of the questions is, how is this realized? I'm not going to the detail because this is, of course, not something we will invent. This is something the radio access networks community will invent on. But of course, we have to basically transport these kind of data and have as well to accept the different architectures that come with that. So how do we address one or the other item? So the higher capacity, so looking into higher carrier frequencies and higher bandwidth, obviously needs an efficient transport system. So of course, we speak about radio access network functional splits as well as point-to-point or point-to-multipoint systems. To better coverage, to achieve a coverage, you always have to take into account the total cost of ownership, because you need to do potential new deployment of fibers, which of course can be in one or the other item a costly thing. You have further to look into the system designs. If you talk about bounded jitter or latency, limited latencies, virtualization obviously is a necessity to have your slicing and automation, that you can handle this on the optical side as well. To ensure availability, you need to have protection and resilience of your network. And the architectures, especially here, edge cloud or far edge cloud, even to provide then the local processing or this large amount of devices that are there, you need to ensure the connectivity, and once again, at lowest cost. So just 1 second as a recap, because the rest of the talk will always focus on these kind of interfaces. I think you all know them obviously here. So that's basically the split, the potential split of your baseband functions and the antenna side, so that you basically distribute things into a central unit, distributed unit, and remote unit, and you have the different high layer splits, the F1, for example, the low layer split, the discussed here by Oran. You can aggregate the different functions at central points or at the antenna sites, and this is what I will talk about in a few seconds. And here, of course, are the details on where the different functional splits can happen, starting at, if you have a very lean remote unit, at the split 8, then going up the stack to 7.2 or 7.3, depending if you have the IFFT and so on. And then as well, right, the F1 that is then higher in the stack. Obviously as well, there's the direction of looking into cloudification of some of these functions that are ongoing, as well as now looking more for 6G about the dynamic reallocation of one or the other function according to the different needs. So right, if we look at the, let's look at the scaling first. We have done a very simple scaling, looking at the maximum rates you could see in a 6G network for a certain, or the transport capacities you could see for the different split points, if you consider different carrier frequency and bandwidth. And obviously, as you can see, the capacity can explode. If you look at this kind of 7 to 20 gigahertz case with a 400 megahertz and the split option 7.2, you can see in the downlink direction almost 600 gigabit per second in the access area. Of course, there are other split points and other functions like the F1 higher in the stack. That's also for different cases, like the sub 6 gigahertz here, the 100 megahertz case, are coming with a very still limited amount of capacity needs. But how do you address all of this? And of course, it's let's say here really the peak that you can see. So one option is to look into point-to-point fiber solutions, and the other solution is to look more for shared networks in the access space. And I come to this. So this is basically how it looks like. One option is obviously, and we have heard about it, to look into this more gray optics. Of course, one thing is that you need to have a lot of fibers that you connect to your remote units. So basically, if you're a fiber-rich operator, then this is an alternative. On the other hand, you can also look into WDM networks, but you need to overcome this typical expensive transceivers. On the other hand, so this way, basically, why do you want to do it? One option, of course, if you go to higher speed point-to-point links, then the beauty is that you can centralize more of your radio functions, but of course you need to pay a price typically on more complex optics. The alternative to this is looking into point-to-multipoint networks, where you can have a potential cost benefit because of fiber sharing. Fewer optical interfaces are needed, and you have this way a lower cost aggregation. However, in this case, you shift radio functions still to the radio side or to the antenna side to benefit basically from the limited capacity needs. Just as an example of what's ongoing in the research, it's basically here one work looking into point-to-point fiber connections with a target to really have the simplest RU implementations, looking here at split option 8. And however, then you need to really work on your optical connectivity. And here I think the speed is indeed not the biggest problem. It's the biggest problem to achieve the right capacity for the given power consumption, complexity, and cost of the link. Because today, as we know, right, we are at terabit on a single wavelength. We are at multiple terabits if we WDM stack it. So what the research that's ongoing? Research that's ongoing is, of course, a simple thing you can still do is looking into intensity modulation, direct detection solutions, with looking into special modulation formats. We have heard about it, or going for higher spectral efficiency, like the POM8 here, where you look into 200 gigabit per second links still with the distance of 10 kilometer. This is one solution. The other solution is where you try to aggregate your radio signal. You basically process them. That's what you see in the lower part. So it's basically called DSP-assisted analog radio over fiber, where you aggregate your radio channel, and then you have an additional aggregation stage to basically multiplex the incoming streams to an optical signal that really is then beneficial for transport. And here it's also realized with a chronic receiver type of solution. So that's one angle. The other is to look into shared networks. Here, obviously, with the goal to optimize then to optimize basically for the shared network. So basically limit the transport resources and have also a bit more complex remote units. So where are we with the TDM PONs? So XGS PON is, so GPON is still the working horse for FTTH services. 10G is available and it has entered the market. 25G is ready and will be deployed in 2021. 50 gigabit per second signals or systems are under standardization in G.HSP at the Q2. And in research, we are working at Bell Labs also already on the 100G solutions, bringing also more flexibility in. And we have recently demonstrated here a 100G PON system based on 25G optics and on digital signal processing that you will need anyhow at 50G, and as well as using optical amplification at the transmitter integrated, because that's another piece that you will see at the 50G as well. So capacities are there. A very quick update on this. So we have basically done traffic analysis for PON for 5G. We have scaled our work. So basically doing here the radio simulation on the left-hand side. And this is really also looking at the air interface and the capacity needs that that you see in reality compared to the peak rates. And this is basically depending on the different split points, it can be lower. So if we talk about F1, it's down, could be down to 20% only. About the peak capacity, and with that knowledge you can design your network for 6G. This is what we have done here on the right hand side for different configuration, different rates, different configuration in the sense of the different gigahertz carrier frequencies, as well as the bandwidth and the MIMO layers. One obvious thing is that the PON can already at 25G use the 6 gigahertz range. It can cope as well with the millimeter waves, and but it's still challenging for the 7 to 20 gigahertz case with the large MIMOs. Obviously, 200G is an alternative to really keep the number of cells that you need to connect with the PON high. Yeah, that's one thing, because that's of course important to have sharing gains. That's as well what you see here. That's basically the categorization, so that there's basically what you have today is 25, 50, what I said is the standardization, and the rest is under research, but it could be a good coincidence then with the 6G that we are ready with higher capacity PONs. Basically coverage, what to coverage. This is also the beauty of in case you have an FTTH network that you own, because then you can have up to 50% reduction in total cost of ownership, because you can do reuse the existing network. And you see on the left-hand side the residential access. These are the green points, and the business and the small cell sites, where you can benefit from these kind of deployment scenarios compared to point-to-point links. One word to latency. Of course, one of the key ingredients to latency in this kind of network scenario is obviously coming from the fiber propagation. You see on the right-hand side the blue part of the allocation. So it's basically, you see a 5 microsecond per kilometer fiber propagation that is there for point-to-point or shared networks. In downstream direction, you face the serialization, deserialization stages, but no particular these PON protocol features that you have in a point-to-multipoint way. So it's very similar to point-to-point link performance. In the upstream direction, it's different because it's a shared network. You need to have you face the media access control challenges and the burst mode from the burst mode nature. So you have to play with or invent on, especially here, the upstream. This is what we are working on. Basically, one thing is to come with low latency max. So we're allowing more the ONU to send or access the channel more often. For example, to send 4 times per frame in ONU. But on the other hand, as well as to increase the cooperation between the radio and the transport system. So talking about here about the cooperative transport interface, so the CTI that is specified in ORAN, that's also taken up already in the standardization Q2 to see and identify the specification of the OLT. And what it does is that the radio scheduler informs the transport about the future needs. And this is, of course, a benefit here that you can play, because then you have no problem about or limited problem about the DBA, so the dynamic assignment process in the upstream direction, because you already know what will come. And that's, of course, just the starting point for me, because you could, of course, think of closer cooperation between radio functions here and the transport functions. That could also be a back channel, for example. One word on slicing and automation. Of course, in shared networks, you need also to provide then the right amount of resources. You need to have basically allow that the slicing that's the automated slicing that's ongoing at the 5G and 6G will probably come with a very special case that you are allowed, that you can transport this. And over here, I've taken the example of the shared network. And this is, of course, also ongoing work that the PON is basically SDN controllable already. And there's also a broadband forum discussion that happened that you can use the Young model to configure the parameters. So there's already a lot of work ongoing, but I also see this as a starting point where you can look at more controller function that you can also integrate over time. One word on network availability. Of course, if we look at how FTTH networks are built, then typically they are not protected. But of course, in the future, if you look at example like smart city or examples like radio connectivity, then this becomes of more and more importance because you have more customers connected. So in this case here, you see active connections in gray, and in red, the standby connections. I'm not going into the details, but of course we will see more connections and more type B and type C connectivity here to really protect or have the network availability. Last word on smart network infrastructure, and of course I could talk probably about on this for a long time, but I just want to highlight here that's a work that's ongoing about a smart city project. It's a German government-funded project on a smart city with basically AI-driven and with the fiber. Here's a key access element, but the point here is, of course, that we also foresee more and more network functions, not only the edge clouds, but also far edge clouds and deep edge clouds that are there, that you don't need to have all the processing centralized, but you can do the processing that you need inside of the infrastructure. And of course, that you basically build then more and more functionality in this kind of network. And of course, as I said, it's about virtualization. So we have to think of that these kind of allocations will be dynamic in the future. Okay, this is just the summary. And I think I will conclude on this. So we have seen increased transport capacity. So there are multiple ways how you can realize it. So we need better transceivers, better optics, better systems, latency, right? So there's a potential for co-integration, let's say from co-location to go to co-integration in the 6G. So increased availability and reliability. So slicing to network, basically to isolate the services, protection, supervision. Power consumption, I haven't talked about this much, but it's, of course, there are functions already. So looking into sleep modes or flexible allocation and optimized transport structures that are already there and not really used today, this could be leveraged. But of course, then this will also bring space or room for more innovations. Cloudification with the dynamic adaptation. So that's of course where AI can play a key role, as well as more joint activities between radio. And then new architectures, what I said, that they are more, foresee more far edge clouds. But of course, what we talk about, we always have to think about the cost of deployments. And this needs to be carefully selected for then a certain or given case. Okay, thanks a lot for your attention.
Thank you, René. We have time for a short question before moving on to the panel. Tommy has raised his hand.
Thank you, a very interesting presentation. I have a question, but potentially we can spill it over to the panel. It is on do you see any evolution on the deployment of deployment costs and hurdles of fiber networks? In Europe, I mean, traditionally backhauling to base station have been dominated by wireless for the deployment and time to deployment, cost and time to deployment. It's my question. I don't know. Maybe you have a comment now. Maybe we can talk more about this in the.
I think it's an absolute reasonable question, because I think so. The GPON basically was ready in time already for backhaul. There have been the pluggables available in the market to some extent, but of course you can see indeed. I think so. What was the progress? First of all, also LTE, the upgrades was basically focused on macro cells. And if you do it, then of course you don't achieve the density you need to really leverage this basically, or to benefit from shared networks, or in particular from PONs. So this way, I believe that you really need to have this kind of densification of your network. So if it comes to small cells, then there is indeed the potential benefit, at least I can say today, from reusing your network infrastructure or from deploying network infrastructures. But of course, you need a certain amount of own use that you can connect. And I think so from our analysis, it's 4 to 8. More helps more, obviously. But I think so, yes, that's still the challenge. But going forward, I think that the PON is ready on one hand. On the other hand, it's of course looking for higher speeds. You have, of course, the drawback that these kind of huge ecosystems is only there to a limited extent, let's say, in this moment. So because I think GPON, as we know, right, there are millions of deployments. And if we look now at 25G, it's just about to start. But of course, also the PON system, last word, the PON system benefits today that it basically follows as well the data center trends. Of course, it needs some adaptations, but so, yeah. So I think that it's an interesting future to really answer your question. Let's see.
Thank you.
Okay, so thank you, René, and thank you all for your attention so far. We will now switch from the presentations to a panel discussion. With participation from the speakers just heard, and it will be joined by one of the workshop organizers, so Tommy Svensson from Chalmers. And before we start the panel discussion, Tommy will give a very short introduction.
Thank you, Patrick. I should go unmuted. Okay, so from my side, I'm active in Hexa-X. I'm leading a distributed massive MIMO task there. So here I would like to do a pitch on if there is a convergence, is a need of convergence, and how should we convert wireless and optical communications to 6G. So I mean, 4G we released the internet, 5G released the things and Internet of Skills. 6G we enable the massiveness here of AI and automation and Internet of Skills and Internet of Senses. But for this, we really need to do holistic research based on holistic performance metrics. So end-to-end latency, end-to-end security, total and efficiency, sustainability, and so on. So thinking about this convergence in this domain, then 40 times we try to do cooperation of base stations, where cooperation nodes, distributed nodes, by relaying and radio over fiber, and then connect to multi-point schemes where we connect them via base stations. 5G, we densified with higher frequencies, meaning that we saw the need for start to reuse the millimeter spectrum also for the access, at least for the early deployment. So towards integrated access and backhaul. And in 6G, we envision to further densify here when we go up on high carrier frequencies, up in millimeter wave / sub-terahertz. And then by then, maybe also need to go away from the cell structure. And what in this domain, what's the role of millimeter wave and optical fibers here? And René touched upon some those things here that I think are interesting to discuss. So baseband splitting aspects, use control splitting. Should we really have the same architecture for those two planes? Signal formats, can we even do some common signal designs for these two domains and so on? We have worked on integrated access and backhaul. I just want to highlight those things we worked on at Chalmers. So a quick glimpse, if you have a fiber connected SDS infrastructure, you need 60 nodes per square kilometer. Fully fiber connected. You can do the same job by if you are fully wireless connected IAB, but then you need in the order of 78 nodes per square kilometer. If you do a 30% mixed fiber and IAB nodes, then you can go down here to 65 or so. And then if you further densify, you can also, via few IAB network, reach very high service coverage probability levels towards 95% here. And then gradually the higher fiber density you have to the small cell base stations, the close to 100% you get. So that's, and these are not advanced, not advanced beamforming and coordination schemes. So there seems to be some potential for IAB connectivity, and then to integrate this with a partial fiber connectivity. Another domain I want to highlight is the potential of using free space optics. It was a hype in the 90s, I know, and there have been some couple of attempts further, and there are ongoing research as well. At Chalmers, we have done some theoretical research where we, due to the fading properties of the 2 millimeter wave NFSO links are different and complementary. By joint communication over these two medias, we can do quite well and reach quite big gains. And here I'm interested if there are any comments further from the experts in the panel and or in the audience on would there be a role for FSO as part of backhaul networking? And then another area we work on is in a big training network called Semantic, the potential for doing end-to-end slicing also with help on the PHY MAC level. So we have this heterogeneous spectrum opportunities and the densification. So can we define also network slicing enablers on the PHY MAC layer in the radio access parts or in the IAB network? So for AGL multi-connectivity, AGL duplexing, and the MIMO channelization, and also how we are defining the slots and the waveform structures, and how to integrate IAB with the dense distributed massive MIMO schemes. So yeah, so we are working a little bit with the optical network group at Chalmers on this now. This work is pictures drawn together with Federico, that was in the meeting now, I think. So how to, in general, how to bring PHY MAC network slicing enablers into an end-to-end network slicing orchestration, where we are adaptively monitoring the do resource creation here and create new paths and opportunities, and be able to communicate that so we can do an end-to-end orchestration. So these were my pitches. I hope I kept my time roughly.
Thank you, Tommy. It's a good presentation. And now we move on to the panels. If all the panelists could turn on their cameras. So, okay, Fabio may have some problem. So with this panel discussion, if you have any questions, please feel free to add it to chat or pose it, and I will moderate the conversation. But we've seen many presentations now presenting both 6G and optical networks. So to go in order, what do you see the main potential of using optical networks for 6G, and what would be the main challenges? So Mikko first, if you have a comment.
So through all the cellular generations, one central feature has been the quite strong increase in the overall traffic, and then obviously here then quite some expectations towards the optical and fixed networks to support the wireless system, and also possibilities from the wireless system to support the optical side as the capacity increases are there on the wireless side.
Thank you. So Fabio, are you with us?
Yes, with you. As I have said in my talk, I think the major difficulty will be kicking off a new ecosystem, because there is a high potential business, but the initial investment is high, and not every system vendor or also component vendor could have the capabilities, also the willingness to risk. So this is something that worries me more about technology issues that I think are addressable and can be overcome.
So thank you. So Carmen, do you have anything to add to respond to this?
For me, I mean, as I said, I mean, the advantage of optical is really the high capacity, and the disadvantage is really the cost, that the investment that operators need. And this is special. I mean, okay, I just presented the core network, but as soon as you go to aggregation and you have all these points, GPONs, NG-PONs, and so on, also reliability there will be an issue. And even investment, I mean, how to offer the high reliability with this PON topology is also an issue. And then this should also be addressed, like laying out more fibers or thinking about the combination of different technologies to increase the reliability.
Thank you. So Renee?
Yeah, well, maybe I also respond already. So I agree. Of course, it's always about the cost. In some countries, right, if they're fiber rich and have already done the deployments, then you see already a lot of fiber and FTTH solutions. So you might have space and spare fiber that you can leverage. So I think that's one angle. The other, of course, for me, it's of course the careful selection of functional splits, and that mobile or RAN and indeed the access networks, also core networks, people work together. Because I think in the past it was not really necessary, because the cost was not the problem. You could buy things from the shelf, especially on optics, but now it becomes more and more important that to find here the right choice, basically, to have a high performant but as well low cost solution.
So Carmen has a comment.
Yeah, I have a comment regarding this fiber that has been laid out. Indeed, in dense urban areas, you have fiber. You have different models. I know that, for example, in Estocolm, the fiber belongs to the city. So I guess that everybody has access. This is not the case here in Munich. And I guess that this is also a business issue. Who owns the fiber and who can access to this fiber?
Can I respond? Yes, so I think that's indeed that's one of the key challenges. Also, if we look in, for example, the example I showed about the smart city network, we have a lot of different networks today. And what do you do if you see what happens basically today is more people come, or operators come and build their own network on top of it. And this is obviously one of the biggest problems we have, because I think we waste resources. And it's indeed, that's a question: who owns it, who deploys it? And this is one of the key things that needs to be answered, I think, across, not only European Union, but.
Thank you. Tommy, you want to?
Any comment on your question?
On the question, or
Yes, well, I think we have a challenge for sustainability in the longer term here. Our community 6G needs to be sustainable, and by doing that, we can also enable other sectors to be sustainable. So I think efficiency is one of the most important aspects of fiber connectivity as much as possible. That's an order of factor 1,000 at least, maybe not in the passive optical networks. Maybe René or some others can comment there. But the further out we can get the fiber and use the wireless for the access and the mobility, and really, that I think that's the way we should work. And here I see maybe we shouldn't have this simple interface. Maybe we should have convergence, so we do certain parts wirelessly, certain parts fiber connected.
Thank you. So, Mikko, how do you see that the Hexa-X project can leverage on these optical solutions for 6G, where they will be employed best?
Yeah, so at the Hexa-X project, this is something that we need to spend effort in the time to come in the project. So we are at early stages, and this workshop is for us to help others understand where we are, and help us to understand then messages and information from the optical side. But certainly there has been like many good material here, looking at we are anyway in the wireless and in the optical side sharing similar kind of challenges. We are part of the same network, delivering to the same end users whatever they need, whatever is the connectivity means. Yeah, here we have a good information on top of which to build, to understand what the possibilities about capacity, about cost issues, and all other important things from latency and reliability and so on.
Thank you. And for the optical experts, what do you think it will be the most important optical aspect for or technology for 6G? So Fabio.
Yes, it is providing high capacity at low cost. This is the holy grail. We have already today in optical networks several terabits transmitted over several thousands of kilometers without regeneration, but this is not something you can use close to your radio unit or your digital unit. So you must ensure similar level of capacity and much lower cost. And this has to do with new technologies. So this is the most important, for sure, the most important challenge we have already in 5G, but even more in 6G. 6G, to conclude, you may use optics also for other purposes. For instance, use optical devices to generate terahertz wave, or to generate very accurate reference, optical beamforming, and so on. But again, I think that this capacity bottleneck in the transport network will remain again the major challenge.
Thank you. And Carmen, do you think we're ready for 6G? What is missing? Is there some specific aspect which will be needed?
Well, as I mentioned in my presentation, there is, well, I am not involved in this project, I have to say, but okay. We still have to have full 5G in order to know also which are the next steps towards 6G. 6G, I mean, it has already been mentioned, the capacity requirements, all this low latency that will move everything even more to the edge, as it is already for 5G. It has been shown that it will have to be like that. reliability, security. I mean, there are so many aspects that they still have to be improved and solved. So there is a lot of room for research. There is a question in the chat if you want.
Okay, yeah. So there's a question from David Larabeti. So what is the extent that 6G will be mostly based on C-RAN? What percentage of base station is envisioned by vendors to rely on fronthaul? Because this seems to be a major driver for 6G optical needs. So who wishes to respond to that one?
Tommy, I can do a comment not from industry perspective percentage, but I can do a comment on the need. When we since 6G we want to boost the capacity and peak data rates and also enable very accurate precision localization and mapping. We see the potential to go on high frequencies, so the upper millimeter wave 100-300 gigahertz. And there the propagations are very harsh. So we're blocking mitigation, so spatial diversity is very important. And in these deployment scenarios, I think distributed massive MIMO systems with a proper split in the function towards C-RAN will be important. But I don't have a comment on the proportion of base station in general. And maybe a vendor can have a comment.
Thank you, Tommy. So, Renee, you want to comment? Or Carmen raised her hand. So
I don't have an answer. I have a question. Which is the density of base stations that will be required in 6G compared with 5G?
So the expectation is that, there is a clear feeling on the trend. So as we are looking for need to ever increasing amounts of data. So there, in order to cope with this increased amount of data, you either need more spectrum or smaller cells or more efficient technology in terms of bits per second per hertz. So most likely we need to look at all of these. So then the obvious answer is that we need more density, but we are at quite the beginning to know how much more density.
Because the problem that it was for 5G is that you had all this platform of 1, 2, 3G base stations that there were some of them interconnected with these microwave links. But then as you move to 4G, they increase the capacity, and then these microwave links are not enough. So you need to start installing more fiber to interconnect some of these base stations. So I guess that towards 5G and even more towards 6G, this increase of base stations will also require even more fiber. That may be in place, but it may not be in place, and then it will incur also in higher investments.
Yeah, I agree with that.
I think this is indeed one of the key challenges. But of course, there are also other technologies, right? Fixed wireless access technologies. So I think it will be probably a traffic or a solution mix. So I think it won't necessarily always be optics. Of course, we have seen now or also discussed about the optical wireless. Yeah, there are some pros and cons. It's research status, but so I think let's see what it always depends, right? There might be a good innovation, and suddenly you have something that you might use in the future.
Tommy has a raised hand.
Yes, I think we maybe also might need to redefine what a base station will be if we are doing different kind of splitting and maybe even adaptively for different slices. But in general, we need to be careful about the radio energy, especially at higher frequencies. So the more spatial granularity we can have of the antennas, and the more fine grain we can be in the control, we can also really utilize the radio energy properly and avoid interference to other areas. So both increase capacity and simplifying the coordination and improving energy efficiency. So depending on the split level, if that is a base station fully on each of those antenna units, or if it is further in, I think that will open research at the moment, and maybe even will be adapted according to the size. So controlled by the program, by software.
Thank you. Any final comment on that before we move on?
Yeah, maybe one final comment about the energy efficiency, because I think it's always good to talk about that and to look at it, but I think we can always try to optimize. That's what we probably have to work on. But if I look at all the use cases we have in mind for 6G and the future, I think it will be a key challenge to talk about energy or power consumption in general, because we talk about higher speeds everywhere. And even if we optimize, so I expect that it will grow and grow and grow. And this will be the key challenge for us, to find ways to at least limit or slow this growth down that we see, at least in these days.
Yeah, I agree. It will be very important. So we're almost out of time now. So thank you all for your attention. But in 30 seconds, could you summarize what is the main message you would like the audience to take? So, Nico, to begin.
6G will come, and the challenges are all the more increasing in terms of what we can deliver, and that will be reflected also on optical networks, and we need to remember sustainability.
Thank you. And Fabio, do you have some summary?
Yes, perhaps the main message is that there will be no longer wireless and optical networks, but the network. And that must be designed, putting together those competences. And this will not be easy because the skills, the background are often different, but this is for sure the future. Whatever will be the solution, cloud versus distributed and so on. But tight integration of technologies is unavoidable in 6G.
Thank you, Fabio. And Carmen, what is your takeaway message?
So we have a long list of challenges to address in order to get to 6G. Mainly, this is what we have discussed during these 2 last hours. So we have to keep working.
Thank you. And Renee, what's your...
Yeah, all right. So I also agree 6G will come. There is the need for flexible and energy efficient optical connectivity, shared networks. And I think one key message is that we need to work together to make this happen indeed, because I'm with Fabio, there's one network. This would be probably the best we could leverage or achieve.
Thank you. And Tommy?
Yes, I can just echo Fabio and René, and that there's a big room here for joint understanding, joint research towards convergence on wireless and fiber optical, and we should find the proper areas where each technology, how to interface and how to mix in an optimal way towards the 6G goals.
Thank you. So we only have a few more minutes. If someone has some concluding remarks or burning question. Otherwise, I would thank you all for attending and bearing with us with these presentation and discussion. And many thanks to the presenters and the panelists taking your time to participate. And thank you all to the organizers for inviting us to this conference. And please enjoy the rest of the ONDM conference.
Thank you.
So I wish you a nice summer.
Thank you.
Bye.
Bye-bye.
Bye-bye.